Alright, gang, here we go. This is for Chem 2 Unit 11. We're going to talk a little bit about entropy on the molecular scale. So previous unit we kind of gave our bare bones definition, or previous part we gave our bare bones definition of entropy, and now we're going to start thinking, well, what does that mean for chemistry? So let's look at this little drawing, this little thing we've got set up. So we've got two gas containers, and there's one of each atom here. There's one blue, one red. Okay, and it's currently closed. Now then they open it and they let it bounce back and forth for a while, and then they close it again. Okay, and there's four possible arrangements. You can have the blue on the left, red on the right, red on the left, blue on the right, both of them back on the left, or both of them back on the right. Okay, so there's four possible arrangements, and look, they call this arrangement. These are called microstates. So remember this for here in a bit when we start. Here in a second when we kind of get a little bit farther into this bit here. So entropy at the molecular level was kind of popularized by this guy here named Maxwell Boltzmann, and we've looked at his stuff in the past. We've called the Boltzmann curves. Remember, like where we had like the number of particles on the y-axis and their kinetic energy on the x-axis, and they kind of made like a curve like this. Remember that? So that was him. That was him. Same guy. All right. So anyway, so let's look at what this means mathematically. So if we let this thing expand, right? Because we had gas and a vacuum over here. We had two molecules on one side. What's the likelihood that they end up there? So what's the likelihood that we get this state again? So what's this? Well, this is 1 out of 4, which is the same thing as saying 1 over 2 quantity squared. So instead, now they're like, okay, well, how often do you just have two atoms bouncing around in chemistry? Not very often. Atoms are ridiculously small. So what if it's 1 mole's worth of gas instead? So what's the likelihood of the entire mole's worth of gas ending on the left-hand side? Well, there's 1 out of 2 chances, right, of the sides. There's one side or the other side, and then there's that many particles, right? 6.02 times 10 to the 23rd. So mathematically, the chances of that happening would be 1 out of 2, right? 1 over 2 to the Avogadro's number, 6.02 times 10 to the 23rd. So the ridiculously small chance, right? Ridiculously small chance, because 1 to that power is just 1, 2 to that power would be some astronomically big number, and so it would be essentially 0. Okay, so notice that when we had just this chance, we had 1 out of 4, but like once we start having gobs and gobs of these guys, the chance of it coming back to its original state is essentially negligible. Okay, so this kind of gives us an idea like of something that we've kind of taken for granted. Whoops, I'm grabbing the wrong stupid box. Okay, throughout our study of science is the idea that gases expand to fill their volume, and the reason they do that is because of entropy. Okay, gases spontaneously fill because they go into the most probable arrangement that has the most chaos or the most randomness, which would be the one where you have equal amounts or approximately equal amounts on both sides. So here again, this is the same idea, but now it's just 1 mole of that gas. So you have gas, all of your gas on the A side, none on the B side. You open that valve, and then now you've got about approximately half and half, right? 0.5 and 0.5. Okay, expanding this gas, this is a spontaneous process, right? This is going to happen all on its own. We've witnessed this happen. If you have a balloon that's got gas in it, you release that, open up, untie, pop that balloon, whatever, poke a hole in it, that gas is going to start escaping from that balloon spontaneously. The balloon is not going to reinflate itself non-spontaneously. This would be a non-spontaneous process. Now, could you reinflate that balloon? Yeah, you just have to put work into it, right? Okay. So essentially this gets us to this idea of called statistical thermodynamics. All right, statistical thermodynamics. I'm going to find a good spot for my head and just leave it there. Okay, and so in statistical thermodynamics, we look at the bulk properties of the substances, so the big picture. Okay, and so we just looked at what happens at the molecular scale, and we have to ask ourselves, well, how does the molecular scale relate? Okay, how does the molecular scale relate to the what we see with the big picture? All right, and so essentially, in order to do that, we have to use statistics, which is essentially what we just did when we're like, okay, well, what's the likelihood of this happening? What's the statistical chance of all of that gas ending up on just one side? It's like statistically impossible. Okay, is essentially what it amounts to. All right, so we can use probability to help us figure out what's going on, and that's essentially what statistical thermodynamics is. Is a burgeoning field, big deal, but also pretty math heavy. Okay, and this gets us to this definition of this microstate idea that we're kind of looking at just a little bit more in the next couple of slides. All right, microstates represent the single possible arrangement of position and kinetic energy of molecules. So I like to think about microstates as like if I'm flipping a coin, there's two possible microstates. There's the microstates where it lands heads up, and there's the microstate where it lands tails up. Right? If I'm rolling a dice, then there's the microstate of 1, and then 1 of 2, 2, 3, 4, 5, and 6. If I roll 2 dice, right, then I've got a whole, I've got way more microstates, right? If I flip 2 coins, now I could get heads and heads, tails and tails, or heads and tails, right? And if those 2 coins were different, then you could have like heads on one, tails on the other, tails on the first for heads on the second, right? And so your number of microstates can get astronomically big, just really quickly with even just simple objects like a couple of coins or a couple of dice. Just imagine how much more complicated it could be once we're looking at individual molecules and we're trying to determine, well, where is it in space, three-dimensional space, and then also how much kinetic energy does it have. So those possible microstates tend to be astronomically big, which is why statistics is so very helpful. So Boltzmann used these microstates in order to get an idea, and so he used this W, right? W in order to represent the number of microstates. Okay, and so essentially, entropy, right? Entropy is the measure of disorder, and so microstates are like all the different arrangements of it, right? So then, therefore, entropy is really just a measure of how many microstates are associated with whatever it is that you're looking at. So if we can get an idea of how many microstates we're looking at, then we can actually measure the entropy, and that's really a huge breakthrough, right? Huge deal when it comes to measuring entropy, because without this idea, measuring entropy can be quite the bear, right? How do we really wrap our heads around it? Before, when we were learning about entropy, we're trying to do it with heat. Well, not all processes involve heat. So how do we measure entropy without that? So anyway, the entropy of a system is really just equal to K times the natural log of that W, the number of microstates of the system. All right. And that K is a constant, and you don't worry about it too much. All right. Since entropy is a state function, we can also use this in order to figure out our total change in entropy. So now we can take our final microstates number minus our initial microstates number, and so we can use this here, and then this last one here, that's just our trick with our logs. Remember, if our log or natural log, if we have them subtracted, then that's the same thing as taking the natural log of them divided by each other, right? And so that's it for this problem, for this part. No practice problems or anything. You just need to have an idea of what microstates are, why they're important, and how they allow us to calculate entropy. All right, that's it. Have a great day. Do practice problems. Let me know if you have any questions, and I'll see you on the flip side.